Okay, so I thought I would do a quick summary of the class today since so many were out, and this will kind of be a good review as well, leading into the exam that will cover a lot of kinematics. Obviously, it's not going to be all kinematics. The old stuff's always still legal, but there's a higher percentage of kinematics on this exam than there will be on the actual College Board exam in May. So we left off here. We were looking at this kind of fake reaction mechanism of making bicycles. And we said if the first step is the slow step, then that's what we call the rate determining step. And of course, it's because nothing else can proceed faster than whatever's running the slowest. And so the slow step always ends up being the rate determining step for the overall reaction. And then of these two examples that I gave you, the first one, the diagram on the left, is one where the rate determining step is the first step, and the one on the right, of course, the second step is the slower step, and therefore the rate determining step because it has the higher activation energy. But turn your attention to the left example, right? The one where the rate determining step is the first one. Notice that above, I can take the elementary reactions, the steps of the reaction mechanism, and I can write a rate law for just that individual step. And if I do so, something kind of powerful happens. For elementary reactions, and only for elementary reactions, because we are running on the assumption that that's what actually happens, that's the collision that actually takes place, it turns out the coefficients in the equation give you the reaction orders directly. And so in this example, the first elementary step is W plus FR yields WFR. Well, that step alone would have a rate law that would be rate equals K concentration of W plus concentration of FR. What's really powerful about that is if we can experimentally determine the overall rate law, as we've been practicing from the experimental data, then we can ask ourselves, does that rate law, the overall rate law that's experimentally determined, match up with or agree with the hypothetical rate law from this elementary first step reaction? And if so, that can give us strong evidence for whether or not the mechanism is actually how the reaction takes place. But there's a huge, huge conditional statement. And this is super important. Make sure you get this in your notes and you study it backwards and forwards. The first step, the overall rate law will be the same rate law as the rate determining step rate law if and only if the first step is the slow step. I'll say it again. The overall rate law for the reaction will be the same as the rate determining steps rate law if and only if that first step is the slow step, the rate determining step. So in this example, is the first step slow? Yes. Therefore, if this reaction mechanism is correct, if it's plausible, if it's possible that it's the way that the reaction is actually progressing, then the overall rate law must agree with the rate law of the rate determining step because it's the first step. Now you may ask, well, what if it's not the first step? Good question. We're going to answer that next unit when we talk about equilibrium. But until then, we can't answer what it is, but we can say conclusively what it's not. It will not be the same as the overall rate law. The overall rate law will not be the same as the rate law of the rate determining step. All right, so two huge, very important new bits of information today. One, if it's an elementary reaction, then the coefficients give you the reaction orders. Remember, that was not true for the overall reaction. If you have the overall reaction, it will not tell you, the coefficients can't tell you anything about the reaction order. We have to determine them experimentally. But if the elementary reaction is how the reaction is actually taking place, if that mechanism is accurate, then the coefficients give you the reaction orders for that step. So in this case, if we found out that this reaction was first order with respect to W and first order with respect to FR, then we might have a valid reaction mechanism. Again, we can never prove our reaction mechanism. We can't say this is the correct mechanism, but there are some that we could certainly eliminate. And if it agrees, we wouldn't be able to eliminate it, so it might be valid. All right, so very, very important. So now let's look at this real quick. In 1467A, it asks what is the molecularity for that elementary reaction. Well, don't let the subscript 2 fool you. That's a diatomic molecule, and it's just one molecule of chlorine. And so that's just one molecule, and so it's unimolecular. And since they told me it's an elementary reaction, I know that the coefficient will give me the reaction order, and so I can write the rate law as rate equals K times the concentration of chlorine raised to the first power, right? Because it's a coefficient of 1, therefore I know it's first order for that elementary step. Now this next one's a little tricky, right? What's the molecularity? It's bimolecular, two things colliding, but when I go to write the rate law, there's a little bit of a pitfall you got to avoid. Remember, I've been screaming at you all year to write your states of matter in your balanced chemical equations, and this is why. It is bimolecular, but the rate law will only be K concentration of OCl minus, which is first order because of the coefficient of 1. But what happened to the H2O? Remember, pure solids and pure liquids don't have concentrations, and so they are not going to affect the rate of the reaction. So he doesn't get to play. And then, of course, the last one is another bimolecular, and they're both gases, so they both have concentrations, no pure solids or pure liquids, and so therefore both of them get to play. Their coefficients give me their reaction orders because it's elementary. If it wasn't elementary, the coefficients wouldn't give me the reaction orders. I'd have to determine it experimentally. All right, so let's look at this example real fast. This is a reaction of A turning into D, and we're proposing that it happens by these 3 steps. A turns into B, and then B turns into C, and then C finally turns into D. Well, what do you notice? What intermediates are there? B and C are intermediates because they get formed and then reused, so they don't appear in the overall process or the overall equation of A to D. And then looking at the diagram, can we order the relative speeds of the steps? Well, from C to D, you'll notice that really tiny activation energy. Therefore, C to D is going to be a fast step. B to C has a really high activation energy, so that's going to be our slow step. And then A to B is somewhere in between, so I'm going to call that medium. And of course, for this reaction then, based on this diagram, we know that B to C is the rate determining step. And therefore, will the rate law of the rate determining step be the overall rate law? The answer is no, emphatically no. The first step has to be slow in order for the overall rate law to be the same rate law as the rate determining step rate law. And then what's the overall delta H or delta E for this process? Well, of course, D ends up higher than A, and so that's a positive delta H. So this overall process is endothermic. If you look at the elementary steps, A to B is also endothermic, B to C is endothermic, and then C to D is exothermic. And when we add up those individual delta H's, they give you the overall delta H, which you'll recall we learned last semester is called Hess's law. It doesn't matter which steps you take or the order of the steps. If you know the individual steps, and since they're state variables, you can just add them up to get the overall change. All right. What about this one? If H2 plus ICl yields HI and HCl, and then that HI then turns around and reacts with more ICl to form iodine and more HCl, what would the overall reaction balanced chemical equation be? Well, we simply ignore intermediates that cancel out, which in this case is HI, and then add what's left. So we'll have an H2 plus 2 ICLs will yield an I2 and 2 HCl's. That's the balanced chemical equation for the overall reaction. The intermediate is HI. And then it says, if the first step is slow and the second one is fast, which rate law do you expect to be observed? Well, once again, that's our thing that if the first step is slow, then the rate determining step rate law will be the overall rate law. And so if the first step is slow, then if I can write a rate law for the first step, that will be the overall rate law, which in this case would be rate equals K, concentration of H2, concentration of ICl. Notice, even though ICl has a coefficient of 2 in the balanced chemical equation, it's first order. And the reason it's first order is because that first step is rate determining, and in that step, there's only one ICl that collides with an H2. And so it's first order. And again, the only way you know that is experimental data. And so this mechanism might be valid because it agrees with the experimental data. Or, I mean, if you got that rate law from the experiment. All right, I'm going to skip ahead of this. Oh, this is just so you can see that last reaction had a catalyst of iodide. Sometimes we don't write iodide in the actual, well, in the overall reaction, we never write the catalyst as a reactant or product because it's going to be on both sides. We're going to use it and then remake it. And so this is how we note that. We write 2 hydrogen peroxides in the presence of iodide ion will form 2 H2Os and oxygen. So that's just a notation thing. Anytime you see something above the arrow, it says that's in the presence of. So sometimes we'll say in the presence of heat, or if there's a catalyst, we'll name it there. All right, this one. The graph tells me that 1 over the concentration of NO gives a straight line when graphed versus time. You immediately now know that this reaction must be second order with respect to NO. Otherwise, it wouldn't have been linear when you graphed the reciprocal of concentration over time. And then notice it says under constant conditions or conditions of constant chloride or chlorine gas. So how do you keep the concentration of chlorine constant? Well, we did it in our experiment, right? We couldn't actually keep it constant. When we reacted the sodium hydroxide with the CVCl, you couldn't actually keep the sodium hydroxide concentration constant, but the way we kept it relatively constant was we used a whole lot more of it. So we used a much greater concentration of the sodium hydroxide. So even though the hydroxide ion concentration and the crystal violet ion concentration were changing the same amounts, their relative amounts were very different. And so any changes in concentration were dramatic for the CV, and they were relatively negligible for the hydroxide. Same thing here. They're going to pretend like chlorine gas concentration stays constant because there's so much more chlorine gas. And so therefore, this tells me the reaction order of NO is second order with respect to NO. And then they ask if that mechanism is consistent. Well, we don't know enough yet to know for sure, but we could have eliminated it perhaps. The slow step is the second step, and so the rate determining step is the second step. And so if that rate law agreed with the overall rate law, then we could say that it must not be consistent, because that would only be the case if it was the slow step was the first step. But we really can only say so much about this because, one, the first step's not the slow step, and we haven't learned how to deal with that yet. But then, two, also, we don't know anything about the reaction order of chlorine. We've established the reaction order of the NO, but we don't know the reaction order of chlorine. So we would need to repeat the experiment and keep the concentration of NO fairly constant by using a large concentration of it and allow chlorine to change concentrations so that we could determine the reaction order of the chlorine separately. So, all right, and then the bottom overall reaction I'm going to carry over to the next page. This is an important skill to be able to do. It tells us that that's the overall reaction, and then it wants us to find out if this mechanism is consistent with the overall reaction. Well, two things have to be true for a reaction mechanism to possibly be valid or to potentially be what's actually happening. One is this: they have to add up to the overall reaction. And so if I try to add these up, do they add up to the overall reaction? Well, your first reaction or your first response might be no, they don't, because there's two Hobers, right, HOBR on the right, and only one Hober on the left. And yet Hober's not in the overall reaction, and neither is Huber. And so if Huber and Hober aren't in the overall reaction, then we know they must be either intermediates or catalysts. In this case, they're produced and then used, so that means they're intermediates. And so Hober has to be an intermediate. So what's wrong? Well, we need more Hober on the left. So the way we fix that is we take the bottom, that was not intended. We take the bottom reaction, the bottom step, and we multiply by 2. If there are really 2 of each of those, then that causes the HOBRs to cancel, which they have to since it's an intermediate, and it also fixes the other problems, right? Now we do have 4 HBRs on the reactant side, and we do have the required 2 bromines on the product side and the 2 waters on the product side, which is what we expected from the overall reaction. So sometimes you have to manipulate, but it does actually add up. And then I went ahead and wrote the rate law for the first step, because that step is elementary, so therefore I can write it as rate equals K concentration of HBr, first order because the coefficient is 1, times the concentration of O2, again first order because the coefficient is 1. And then it asks, right, based on the experimentally determined rate law, which step is rate determining? Well, the way I know this is they told me that I find the reaction to be first order with respect to HBr and first order with respect to O2 in the question. So they told me the overall rate law is K HBr O2. Well, the first step has the same rate law. The rate law of the first step is K HBr O2 as well. So since the two agree, the first step must be the rate determining step, because the rate determining step rate law is the same as the overall rate law if and only if the first step is rate determining. And so now I know that this mechanism is valid, and it would agree with, if the first step is the slow step, it would agree with the overall reaction rate order, rate law, and therefore this mechanism is potentially a valid one. All right, and then I want to skip ahead to one more thing. Speaking of seeing if a proposed mechanism is valid, we have this guy. If we have this overall reaction and we have this proposed mechanism, we could first ask ourselves, is it valid in that do those two add up to the overall? And of course, we do have an NO3 intermediate, so after we cancel that out, they do add up. And then if I additionally gave you this data, we said we experimentally determined that the first step is slow, the second step is fast, and then here is a table of initial rates given some initial concentrations. Can we determine the overall rate law from this data? Well, of course we can, right? When NO2 stayed constant and CO doubled, the rate stayed the same. So the reaction order of CO is 0. When CO stayed the same and NO2 doubled, the rate quadrupled. Therefore, it's second order in NO2. So the overall rate law is K NO2 squared. Well, does that agree with the first step rate law, since the first step rate law since the first step is slow? If the first step rate law, which is the rate determining step rate law, agrees with the overall rate law, then the mechanism might be valid. And if you take the rate law of that first step, it's going to be rate equals K concentration of NO2 squared, because there's 2 of them, and therefore that agrees with the overall rate law, and therefore this is potentially the mechanism that is going on in the reaction. Once again, we can never prove a mechanism is right. We can only disprove alternatives. So we can say this can't be the mechanism. We can never say this is the mechanism. But if enough times we prove that alternatives are not the mechanism and we can't disprove that this is the mechanism, that's when we start to assume, well, okay, maybe this is the actual mechanism, what's actually taking place behind the scenes. All right, so again, in summary, the new stuff you missed from today. When it's an elementary reaction, and only when it's an elementary reaction, you can know the reaction order from the coefficient. You cannot have confidence that the coefficient is the reaction order unless you know that it's an elementary reaction. How do you know it's an elementary reaction? We have to tell you. We either have to tell you by making it a part of a reaction mechanism, or we have to explicitly say this is an elementary reaction. Right? And then the other one, if and only if the first step is slow, then the overall rate law will be the same rate law as the rate determining step rate law. So again, you can use that either to but to support that the first step is slow if they do agree, or if you know the first step is not slow, then they can't agree, because they will only agree if and only if the first step is slow. All right, well, keep studying. Don't forget to study old stuff as well. And let me know if you have any questions.